Today we're going to talk about something called impulse. And impulse is going to be familiar to us as just a new term. All that impulse means is the change in momentum during a collision. Okay, and it doesn't even necessarily have to be during a collision, but during some change, right? Any change in momentum is what we call the impulse. There's a couple different ways we can solve for impulse. Okay, we've seen this equation before, right? Momentum is equal to force times change in time, or is this one new for us? Okay, pretty close. So a rearranged version of one of the equations we have so far. Okay, so delta P is change in momentum, which there means impulse, therefore means impulse. So force times the change in time would give us that. This impulse equation applies to each object in our collision. So both of these objects would undergo a change in momentum. Okay. What would probably be the difference between those two numbers, or those two values? Right? If there's a change in momentum for each object, what would be the only difference between that number? What? The force would be the same. I'm just really talking direction, right? If there's a collision in which they're heading opposite directions, we might see a change in momentum that are in opposite directions, okay? But usually the same value, okay? Impulse is helpful when we're looking at very, very short periods of time. So when we look for impulse, we're really only looking at the exact moment of contact, or the exact moment of that collision, because we want to see the real change in momentum that's happening, right? The transfer of energy and that transfer of momentum. So when we look at impulse, it's usually for a really short amount of time. Sometimes we'll stretch it out and look over a longer period of time, but for the most part, we're really looking at the moment of collision here, or the moment of contact. Okay, so this is another way that we can solve for impulse. Mass times the change in velocity. This equation should look very familiar. And then what am I doing right down here? Setting those two equal to each other, right? If they're both equal to delta P, or both equal to impulse, I can set these two equations equal to each other. And we'll do that pretty often. With this impulse section. What's that? It's not that bad. But think about it. Do we really ever have delta T, or is it usually just T? It's usually just T, right? Usually. We don't say it starts at 5 seconds, ends at 10 seconds. That's not usually how it goes. Delta V, we do see a delta V. You need to be careful with initial and final velocity, right? If something comes to a stop, what would our final velocity be? Zero. So sometimes that makes our impulse then negative, right? We have a negative change in velocity. Let's go ahead and try this problem for impulse. This is asking us for the force required to bring this object to a stop. Does it mention impulse anywhere in this question? No. Does it mention momentum even at all in this question? No. So you have to understand how these things tie together. Okay, so force is what we're solving for. Mass is 75. Velocity is 44. And is that initial velocity or final velocity? Initial. Okay, and time here is 2.1. Okay, so I don't need to bother doing two separate equations here. I can set these two equal to each other. So F delta T is equal to M delta V. We're solving for force. Our time is 2.1. Mass is 75. And delta V is now good. 0 minus 44, or negative 44 there. So that gives me negative 3,300 on this side. I'll divide that by 2.1. And my force now is negative 1571.4. What's our units for force? Newtons, good. Always newtons. So what does that tell me that my force is negative? Yeah, it's in the opposite direction of the motion, right? So if my object's going this way, my force is being applied there to slow it down. Okay, so the negative force does make a difference, right? Forces are vectors, so they have to have magnitude and direction. That negative there is telling us the direction that it's going in. Okay, any questions here? Things that make other things slow down usually give us a negative force, right? This is opposing our motion. All right, very good. Go ahead and try this one. It's really as easy as it seems. Okay, what's the change momentum of an object that's acted on by a 64 Newton force for 3 seconds? What do you think? 64 newtons times 3 seconds. Newton seconds, or what's our other unit for momentum? Kilogram meters per second, right? Either of these would work for momentum, right? This is mass times velocity. This is force times time. Right? Those two units mean the same thing. I know that momentum units are not as clean as what we would like them to be. Okay, so we can look at this a couple different ways. It started from a height of 8.4 meters. Is it going to fall all the way to the ground here? No, it only falls 3 meters. So our final height is really 5.4 meters. Okay, we can look at this a couple different ways, but I want to get all of our numbers out there first. Does it start with a velocity? No, right? It's dropped. So that means our initial velocity is 0. We need to find the velocity at this point. Right? So we need to solve for final velocity. What do we know about the acceleration in the vertical direction? Always negative 9.8. Okay, so do we have a kinematics equation that we can use to solve here for velocity? The answer is yes. We need to figure out which one that is. Rack your brain for your kinematics equations. That's one of them, not this one, though. Oh, no, you're right, Kelsey. You're right. You're right. That's all you remember of the equation? That's right. I was off one. V squared equals VO squared plus 2A y final minus y initial. Okay, good. We want to solve for velocity. We know this is 0. Now here we can either put 8.5 minus 5.5, or we know it's fallen a total of 3 meters, so I'm just going to put 3 meters in there. Okay? You could do 8.4 minus 5.4, or since you know it has fallen a difference of 3 meters, you can put that in there as well. That delta y should really be a negative 3, right? Because our final distance was 5.4. This was 8.4. We can't have a negative for this term, so we have to make sure that comes out positive. Okay, it's fallen downward 3 meters. Okay, why do we have a negative final velocity here? Going in the downward direction. Good. Okay, we want to find the momentum after it has fallen 3 meters. So what equation for change in momentum or for impulse should we use here? M delta V, right? Okay, so I would take delta P. Since it starts at the beginning with no momentum, right, we're finding the change in momentum, M times delta V. Mass, which is 4.3. Our change in velocity was negative 7.66 minus 0, right? It started with 0 initial velocity there. Okay, so we get a value of negative 33. Okay, questions here about impulse? Do we need to worry about solving for the acceleration? No, right? Don't let those things throw you off. Okay, force is 25, time is 0.23, and velocity final is 1.29. Okay, since it's telling us starting from rest, our initial velocity here is 0, so that makes our delta V part really easy. Okay, everybody get it to come out at 4.46? Hopefully, since I gave you the answer. Okay. Okay. All right. We're going to go back to collisions now a little bit, and I'm going to give you a couple more equations you can use to solve for collisions. Okay, I know you just love more equations. Okay. We've talked about the conservation of momentum within a collision. Now we're going to talk more about the conservation of energy. Okay, is there a loss of energy or a transfer of energy or a change, a loss of energy to the system in a collision? Yes or no? Okay, so in elastic collisions, for a perfectly 100% elastic collision, that means everything goes the way it should. There's no loss of energy. Okay, and when we say loss of energy, do I mean that it completely just disappears into nowhere? What probably happens if I say there's a loss of energy in that collision? Yeah, it's changing forms, or it's going to the system rather than just within the collision, right? So we have some sort of a transfer, but it's not just disappearing to nowhere. Okay. So in an elastic collision, our kinetic energy is conserved, which means kinetic energy before equals kinetic energy after. Okay. So what do these equations look like? No. Kinetic energy of the first plus kinetic energy of the second object equals kinetic energy of the first prime plus kinetic energy of the second prime. You just need that bottom one. Just the bottom one, not this guy right here. Right, this is the expanded version. In order for an object to have kinetic energy, what has to be happening? Has got to be in motion. Good. if we look at this equation, and we look at the regular equation that we have for collisions, is there much difference? Are the variables any different? No, right? The first equation that we got for collisions is m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Okay, so unless they specifically ask for the kinetic energy of the system before and kinetic energy of the system after, there's really no reason for us to use this equation to solve just for the velocity of an object or the mass of an object, right? We can use our other equations for that. This equation would be specifically if we asked for what's the kinetic energy of object 1 or the kinetic energy of object 2 or whatever that might be. Okay, but if it's just asking for mass or velocity like our regular collisions, there's no real reason to use this equation because it's just more complicated, right? m1v1 plus m2v2 is more simple. Okay, but this is for looking at the conservation of energy rather than just momentum. Okay, these two equations, I know you guys are really drunk today, okay? These two equations we can use to solve for the velocity of an object after collision without the other object's final velocity. So I can walk you through how we got to these equations, but I don't want to, and I don't care, and you don't care. Okay, so these equations have v1 prime, what we're solving for here, but do you see v2 prime anywhere in this equation? No. Okay, same with this one. This is solving for v2 prime, but v1 prime is nowhere in this equation. Okay, so this allows us to do some manipulating here to get to that final equation so we can solve for these. And this equation is derived from that kinetic energy equation. Okay, so they are kind of connected here. Okay, are we ready to try some? All right. Refocus. Okay, two billiard balls are moving toward each other. The one moving left has a mass of 8 kilograms at a speed of 2 meters per second. The one moving right has a mass of 0.9 kilograms and a speed of 3 meters per second. So the one moving to the right, is that the positive direction or the negative direction? Positive. So that means the one moving left needs to be negative. Okay, so -2. Pinky here is +3. Okay, we want to find each of their final velocities. Can we do that using our regular m1v1 plus m2v2, m1v1 prime, m2v2 prime equation? No, we cannot. We cannot because we don't have either v1 prime or v2 prime. So we have to use those two new equations that I gave you to solve for those. Okay, so let's solve v1 prime first. Okay, which would you rather consider the first object or the second object? First one is blue because it was listed first? Yes. Okay, so this would be m1, which is 0.8, and v1 equals -2. And we don't know what v1 prime is equal to. m2 equals 0.9, v2 is +3, and v2 prime we don't know. Okay, so using that equation to solve for v1 prime, it's M1 minus M2, so 0.8 minus 0.9 times V1, which is negative 2, plus 2 times M2 times V2. Okay, do we see where these numbers are coming from? Match the equation that you have, hopefully. All of that's going to be over M1 plus M2. Okay, any questions about where these numbers came from? Okay, let's go ahead and plug that in. You solve for V1 prime, can you go plug that into your regular 4-term equation? You can do that. Okay, the only problem is if you solve V1 prime wrong, then you're going to solve V2 prime wrong. Okay? Do we agree with 3.3 or did I plug it in wrong? No. Good? Okay, let's solve for V2 prime now. You could solve it either way, and we'll see if we match. I'm going to use the new equation that we got without V1 prime. Agreed? Okay. Go ahead and try this one on your own. We should have gotten 0.7 for M1 and 2.2 for M2. Okay? Very good. We saw on our lab simulation, I hope that you saw this, if objects have equal masses and we have a perfectly elastic collision, what happens to those two velocities? They just switch, right? In a perfectly elastic collision, we see that no energy is lost. It's all going to be transferred. So if they have equal masses, we're going to see a perfect switch in velocities, right? They're going to completely transfer all of that energy. That only works if they have equal masses. If they don't, we have to go ahead and plug that into the equation. Okay, I wanted to make that little last point about elastic collisions. In inelastic collisions, we don't have a conservation of energy. What we do is in an inelastic collision, we have some sort of a transformation. So it either becomes thermal energy, heat energy, same thing, or even other types, okay, that we're really not going to get into. But you'll see some sort of a transformation. Okay, so energy is not conserved in an inelastic collision. Okay. When we talk about inelastic collisions, we're able to calculate the amount of kinetic energy that's lost using that kinetic of the first plus kinetic of the second would equal kinetic total, right? We would be able to calculate how much is lost. We're not going to go through any of those, but you do have the ability to calculate that with that kinetic energy set of equations that I gave you today. Okay? That's where we're going to stop today. Next.